Hello everyone! Let's create an effect that resembles boiling lava viewed from above, which can be useful for various top-down games. It's also a great demonstration of using four-dimensional noise and slicing it into three-dimensional layers, resulting in the characteristic flowing lava animation. So let's get started. This time, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up for this kind of shader. Right-clicking the scenes folder, create new scene, and it's going to be user interface, and let's call it lava. Simple as that, okay. And I'll right-click the root node and add child node of the type colorrect. Now let's go to the inspector and change the background color to black. I'll expand layout transform and set the size to Full HD 1920 by 1080. Okay, and let's scroll down to the materials section where I create a new shader material. Click it and add a new shader, which is type shader, mode canvas item. The name is lava.gg shader, and I'll put it to the shaders folder. Shaders, okay, create, and it was automatically opened in the shader editor because I am using Godot 4.7.1. Okay, and as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function. So I'm deleting vertex, and I'm deleting the commented out light, Ctrl S to save. And here we go. I'll start by adding a resolution parameter, which we'll need to recalculate the aspect ratio, since we want the effect to appear always the same. Let's do it here. Uniform vec2 resolution equals vec2, and the initial value is 1920 and 1080, our full HD resolution of the colorrect. Okay, I'll also go ahead and write the usual beginning of the fragment function. To make the object appear in the center, we shift the coordinate origin and adjust the aspect ratio. So right here, deleting the comment and vec2 uv equals uv minus 0.5, and uv dot x is multiplied by resolution x divided by resolution dot y. Alright, next we need two more parameters, a zoom factor and an animation speed. So I'll go back to the uniform parameters and add them. Uniform float zoom with a hint range, and the initial zoom will be 4, for instance, and it goes from, let's say, 0.01 and to 40 with the step 0.01. Okay, and now the speed parameter, uniform float speed with another hint range and initial speed I set to 0.6, and it goes from 0 to, let's say, 4, again with a step 0.01. Now we can return to the fragment function and add the code that makes use of these parameters. It will be very simple as usual. UV is multiplied by the zoom factor and too many O's, sorry, zoom, and float time equals internal time times the speed parameter. So, to complete the basic Bezier skeleton, all that's left is to perform some calculation and display its result. This time, we'll be working with a four-dimensional fractal generated using fractal Brownian motion, or FBM for short, a technique we've already used many times in previous tutorials. I'll explain how the algorithm works shortly. For now, it's enough to create an empty function called FBM FBM. Let's do it right above the fragment function. So, no, it's vectors returns vector 4 FBM, and the parameter is vec3p as a point in the three-dimensional space. And now vec4, let's call it fractal, starts as 0 vector, so vector 4 with a 0 parameter, and I'll simply return fractal. Okay, and we will then call this function from the fragment function like this, scrolling down, and the next line will be vec4 result equals our FBM function, and the parameter is vector 3 that's composed of the UV coordinates, which is vector 4, and time as the third component. Okay, too many brackets, sorry. Finally, we'll send the result to the output, which is the color variable and also of type vec4. So color equals result simply. Okay. Very well, and that's our first version of the shader. It's not too exciting, of course, as it doesn't display anything yet, because the FBM function always returns a 0 vector, but we'll gradually build it into something much more interesting. So, simply put, the idea behind the FBM algorithm is to perform a certain calculation multiple times using different parameters and then combine the results. To control how many iterations are performed, we'll define the iteration count as a constant. So I'm scrolling up to the uniform parameter section, and after that, let's add const int integer octaves equals 5. As I explained in the previous video, using a constant is better than introducing another uniform parameter in this case, because it allows the compiler to optimize the loops, especially on mobile platforms. So how are we going to proceed? As you can read in many sources, including the excellent book, The Book of Shaders website, fractal Brownian motion is based on repeated iterations in which values such as amplitude, frequency, and others are modified each time. In practice, you can adjust almost any variables that accumulate nicely into the final result from one iteration to the next. In our case, we'll use the following variables. So let's go to the FBM function and add these lines. Vec4 swizzle equals vec4 again a 0 vector, then float amplitude equals 1, and float warp equals 0. Okay, so the least familiar one is probably swizzle, this one, because I don't think we've ever used anything like this in any of our previous FBM implementations. The name comes from swizzling, which refers to rearranging the order of a vector's components. Since we want to generate a vector 4 from an input vector 3, this operation will be very useful. We'll see exactly how it works when we implement the loop. So let's start. Let's add the loop skeleton. For int I equals 0, I less than octaves, and I plus plus, and the body is currently blank. I should probably mention at this point that the code for this shader may be even more complex than usual. However, the result we saw at the beginning of the video is definitely worth the extra effort. And in the end, you don't have to understand every implementation detail to use the shader effectively. You only need to know how to control the effect using its parameters. So let's start the implementation. Before we do, we need to write at least the skeleton of the function that we'll call during each iterations, and it will look like this. Let's scroll up, and before the FBM function, I will add these lines. Vec4, and I'll call it decorrelated noise, with the parameter, again, vec3p, the point, and at this moment it will return simply vec4 p, and the final component will be 0. Okay, we'll improve this function later, so it actually performs the intended calculation. For now, let's return to the FBM function and our loop. The first step is to calculate the value returned by our new function. So inside the loop, I'll write this vec for n equals the correlated noise applied on the vector p. For the simplest possible implementation, we'll just multiply this value by the amplitude variable and store the result in a fractal accumulator. So fractal is increased by plus equals n times amplitude. Okay, so we'll stop here for a moment because any further improvements would be much more meaningful if we could actually see some results. To make that happen, the decorrelated noise function needs to return a real noise. So let's work on that first, starting by adding a constant that contains an array of all 8 vertices of the unit cube. Okay, and I think we can expand this window so more of the code can be visible. And let's add a constant right after the constant int octaves. Const vec3 cube, and it's an array with 8 components, and it equals vec3 and 8 in the square brackets, and now the body of this array in normal brackets. And let's do it on 2 lines. So vec3 0 0 0. Yes, I could use just 1 0, but I will then change these components to simulate the vertices of the cube, so it's better if we always use 3 numbers. And vec3, and this time 0 1 0. And I will copy this part and paste it twice and change the value. So the third one is vec3 1 0 0, and the last one would be 1 1 0. Okay, that's the first line, and now I will copy and paste and add a comma after the first one, and the second row will be 0 0 1 0 1 1 1 0 1 and 1 1 1. Okay, let me just check the values. 0 0 0 1 0 1. I mean 0 1 0 1 0 0 1 1 0. Yeah, this should be correct. Okay, so this array will serve as the foundation of an algorithm which, with the rather long name, linearly interpolated value noise on the unit lattice. It's essentially a 3-dimensional variant of Perlin noise that allows us to generate smooth 4-dimensional noise from a 3-dimensional input. We can then slice this 4-dimensional chaos into 3-dimensional layers and display combinations of those layers. In short, we'll pass the current pixel's UV coordinates together with the time value together as a 3-dimensional vector, which we are already doing here in the fragment function. So this vector we pass to the function and will be rewarded with animated lava. To use the shader effectively, you really don't need to know anything more than that. This means you don't need to understand every detail of the code I'm about to write either. I originally experimented with common functions such as fract, mod, floor, and similar ones, but after some time of running the calculations, the result always started producing sharp edges and discontinuities, which significantly spoiled the overall effect. I couldn't find a way to solve this problem, so I eventually switched to a completely different algorithm called the permuted congruential generator. Since this is a bit of a mouthful, I'll simply refer to it as PCG. I won't burden you with all the details because I don't fully understand every aspect of it myself yet. The important thing is that this algorithm works with 32-bit unsigned integers and relies on operations such as bit shifts, XOR, and similar integer operations. As a result, it doesn't suffer from the rounding errors associated with floating point arithmetic and should work reliably even on mobile platforms. But enough theory. Let's get to the code. First, I'll write a function that performs the permutation using the operations I just mentioned. So let's scroll up after the constants and I will add this. It's gonna be a little longer. UVEC4, yeah, I'll explain that shortly. PCG for D with the parameter UVEC for V for the vector or vertex, more like. And V equals V times, and now two long numbers, 1664 525, and the suffix u, again I'll explain it shortly, plus an even longer number, 1013 90423 and suffix u. Okay, and several calculations follow. V dot x is increased by V dot y times V dot w. V dot y is increased by V dot z times V dot x. V dot x. V dot z is increased by V dot x times V dot z. V dot y. And V dot w is increased by V dot y times V dot z. Yeah, definitely. If you are not sure about this and possible typos, I strongly recommend to copy the final code from the Godot shader pack product because I am just struggling with not doing the typos either. So, and now V is, this is the XOR operation, I think, and V is shifted by 16 U. Okay, and for more lines of accumulation, V dot x is increased by V dot y. Wait a minute. Yeah, I think we can copy and paste these lines because they are completely the same. Yeah, very interesting algorithm indeed. And the final will simply return the resulting vector v. Okay, notice that I used UVEC4 and U suffixes in the numbers. The reason is that bitwise operations wouldn't produce the expected results if we were working with signed integers, like this shift and XOR and other operations. These constants, this one and this one, aren't arbitrary either. they have a precise mathematical meaning that I won't go into here. What's important is that this function forms the basis of the hash for 3 function, which I'll write next. Okay, let's continue with rather boring but still very important code. vec4 hash for 3, and the parameter is vec3p. Okay, if you've been watching our tutorials in the past, you know that these numbers, in this case 4, 3, means that we are returning a 4-dimensional value, and the 3-dimensional value is the input parameter. Okay, and now uvec4 v, now I'm building the input parameter for the PCG4D function, so uvec4 v equals uvec4, and the components will be the following. Sorry, semicolon right here. So the first one, and this is a new thing either, float bits to uint, this function, and the parameter is p.x. Okay, now I will copy and paste this line 3 times. So I get 4 arguments and delete the comma after the last one. And let's change the components of the vector p. p.y, p.z, and finally, to get 4 different seeds for this function, let's use a simple sum. p.x plus p.y plus p.z. Okay, so we prepare the vector v, which we'll now use to get the result from the PCG4D function. So v equals PCG4D, and argument is a vector v again. And now let's return a normal vector. This one is not with the prefix u, so we need to do some casting and also a normalization. So return vec4 of the vector v, which converts the uvec to simple vec and divide it by the last long number I'm going to use in this tutorial, 4294 9 6 7 2 9 5.0. This is actually 2 to the power of 32 minus 1, the biggest possible 32-bit unsigned number, times 2 minus 1. Okay, so the floats bit to uint function, these ones, is something I haven't used before. It's a very interesting function that converts a floating point value into its 32-bit binary representation, consisting of the sign, exponent, and mantissa, and returns that bit pattern as a 32-bit unsigned integer. This infographic you are currently looking at shows the result it produces for input value 3 as an example, and illustrates how the value is obtained. You will also notice that the output value of the hash 4.3 function is a regular vec4, as I mentioned. So we convert the uvec to a simple vec, normalize it by dividing it by the maximum 32-bit unsigned integer, and then remap the result to the range from -1 to 1, hence multiplying by 2 and subtracting 1. Now it's time to implement the noise function, where we'll interpolate the previously calculated values across the vertices of a unit cube. As I mentioned earlier, this is a variation of Perlin noise, so we'll be using we'll be using the floor fract and various combinations of the mix function. Okay, so right after hash 4.3 and before the correlated noise, I am adding the function called vec4 noise with the parameter vec3, and let's call it x the input parameter. And now, as I mentioned, the parallel noise, so you may remember from previous tutorials that it contains floor and frag function and a start, so vec3 p, the point is floor of our x parameter, and let's call it vec3 fr, because it's supposed to be a fractional part. And since we're working with vectors and want a really smooth lava, let's smooth it out at this moment as well. So smooth tab of 0, 1, and the parameter is fract of x. Okay, this is the preparation, and now we are going to write several mix functions to interpolate. So let's start first with something like a first level. We will blend pairs of corners of along the x-axis. So 8 corners of the unit cube will produce 4 values. This is the first one, vec4, and I'll call it L1C1. Okay, and it equals mix of hash for 3, and the argument is p plus cube, our array of the index 0. Okay, and hash for 3 of p and cube 2. All right, and fr dot x as the value to interpolate. Okay, so this is the first one. Let me just check if I did it right. Something is not right. Let's verify what exactly is not okay. Too many arguments. Vec3. Okay, so sure, this is supposed to be plus, not a comma. Now it's correct. And as I said, we'll be working on 8 corners, 8 vertices, and produce 4 values. So I'll copy and paste 3 times. 1, 2, 3, and rename this to L1C2, L1C3, and L1C4. And we need to change the indices of the cube array. So this is 1 and 3. Okay, the third line will be 4, 4 and 6, and the last one 5 and 7. Okay, and now the level 2, which means we will blend these values along the y-axis and will produce 2 new values. So I think I just add some comments. Level 1 and now level 2. And let's do this. Vec4 L2 C1 equals mix of L1 C1, L1 C2, and this time fr dot y. So this is the front face, and now let's do the back face, and again I'll copy and paste. So the second vector is L2C2, and the arguments of the mix function will be L1C3, L1C4, and again fr.y. So we have front face and back face. And finally, the level 3 is simply the mix of these two values into one return value. Level 3. And as I said, let's return mix of L2C1, L2C2, and finally fr.z. Okay, great. Now that we've made it through the least exciting part of the tutorial, we can return to the decorrelated noise function and replace the placeholder with a call to the noise function. So let's go here and I'll replace it with noise with the argument p. Okay, and let's take a look. We are already seeing something visible. It's not exactly the lava we were aiming for, but we are definitely heading in the right direction. Let's go back to the FBM function. I'll just expand this again. Sorry. No, this is a pin. Expand that again. And let's find the last line inside the loop and improve it by using the absolute value. So where was it? Here, fractal. And so instead of n, I'll use abs of n. Okay, and the image should change a little bit. Let's take a look. Okay, so our effect already looks more interesting. We'll continue refining it, but first I'll add a few uniform parameters that are essential for fine-tuning the effect. These control various types of distortion, as well as the brightness, sharpness, contrast, and emission. Okay, it seems the video is already 30 minutes long and we are still working on helper functions. But don't worry, I'm pretty sure that the final length won't be longer than 1 hour. Okay, so let's add the mentioned uniform parameters at the top of the code. Uniform float, warp, primary, with a hint range and 0.2 is the initial value, and it goes from 0 to 4 with a step point 0, 1. Next one is uniform float warp secondary with another hint range, and this time the initial value is 0.3, and again it goes from 0 to 4 with the step point 0, 1. These two variables, these two parameters are supposed to control the final shape of the lava pattern. So basically, they'll be used in two different parts of the algorithm, and we can work with them to, as I said, shape the plasma structure. Okay, and now, as I mentioned, brightness, sharpness, contrast, and emission. So uniform float brightness with a hint range and the initial value 0.5, and brightness, it goes from 0 to 1 with the step point 0, 1, and let's save some time, so copy and paste this line 3 times, 1, 2, 3, and I'll rename it to sharpness, contrast, and emission. Yeah, okay, and let's fix the values. So for the sharpness, the default value is 2. For the contrast, 1.3, and 1.5 for the emission. And the ranges, sharpness goes from 0 to 4, and so does the contrast. And finally, the emission from 0 to 10. And sorry, I think the sharpness goes from 1 and the contrast from 0.1. Okay, and let's fix the default values in the inspector. So I'm expanding shader parameters and pressing these reset icons. Okay, now that we have the parameters in place, we can continue by rearranging the components of the n vector. Let's go back to the function fbm. Okay, this n vector. Oh, this is the swizzling I mentioned earlier. We won't see any visual change just yet, but it will become useful in a moment. So right after the fractal equals is increased by this. Let's write the new line. Swizzle is increased by n, and now the swizzling dot zwxy times amplitude again. Okay. And basically it will feed the secondary warp, which is driven by the warp secondary parameter. Okay, next we'll recalculate the amplitude using the brightness parameter, and this time we will see a visible difference. So let me just show the 2D editor again and find the FBM function here, and right after that amplitude is multiplied by brightness. Okay, yeah, something definitely changed. Then, following the standard principles of the FBM algorithm, we will update the remaining variables. So I am adding this line. Warp is increased by 1 and P is multiplied by sharpness. Okay, so the effect has changed again, bringing it one step closer to the lava we are trying to create. I will add a few more lines with similar calculations to smooth out the structure. So let's continue. P is increased by and n dot x, y, z times warp primary, our first parameter, times warp variable. Then P is increased by swizzle of x, y, z times warp secondary. And finally, P dot z is multiplied by fractal dot w times 0.5 plus 0.5 and multiplied by some low value 0.015. Okay, yeah, I think we are getting very close. However, the motion still seems a bit too regular and periodic, so it's finally time to put the decorrelated noise function to use to the use we originally intended. Instead of calculating a single noise value, let me find that here. Instead of calculating a single noise value, we'll combine two noise values with different parameters. So I will just add a bracket here and noise P plus noise, and this time a different argument, P plus some number, for example 120.5, and let's multiply the result by 0.5 to make an average. Okay, now it looks really interesting. It still resembles an oil spill more than a boiling lava, but even in this form, it could be useful for some projects. So let's experiment with the parameters a bit. Let's go to the inspector, and for example, I'll change the zoom. Now it's farther. Now it's closer. Interesting patterns are appearing. Or speed, of course, it can be much faster, or we can stop it completely. And our primary, so yet the structure is definitely changing somehow. Let's reset brightness, less, more. Yeah, very nice. Or sharpness. Now it's sharper. Now it's very blurry. And contrast, of course, higher, lower. Sorry, contrast is not used yet, and neither is the emission. So let's wait with the last two parameters for a later phase. Okay, but we are not done yet, though. There is one final detail left, and coloring the effect correctly. So I'll add the last two uniform parameters, and I'll expand this again and scroll up to do it. And I'll add two color parameters, uniform vec3 RGB color core, the main one, with the hint source color, and the initial color will be vec3 1.2, 0, and 0. Okay, as you can see, this value exceeds the usual 0 to 1 range, and that's because we can use it for HDR. Displaying the HDR values, it will shine a bit more. And as we know, source color is the hint to tell the inspector to show the color picker. All right, and then the color edge will be the second parameter, uniform vec3 color edge, to emphasize the edges of the plasma pattern. Again, source color, and the initial value is this time vec3 0.9, 0.7, and 0.3. Okay. And now it's time to add the coloring. I'll insert the new lines at the very end of the fragment function. First, I'll define a variable called heat. And once again, we'll make use of swizzling. So let's go really after the final color, because after that we will delete this line. And let's do it. Float heat equals dot product of result dot X, Y, Z, W. Okay, that's not exactly swizzling. I could have simply leave this suffix out, but let's keep it there. And a result Y, X, W, X. Yeah, for example, this thing, and multiplied by 0.5 to give it some better looking value. Okay, what exactly is wrong? Result. I've written a result here. Sorry, a result. Now this is correct, and of course, let's fix it here as well. All right, and next I'll use this heat value together with other parameters to generate the final color. So vec3 color equals heat times mix of color core and color edge, and the weight value is heat. And let's multiply that by our emission value. Okay, and then we'll assign it to the output variable color. And let's show the result again, because we will change it right now. Color in capital letters equals vec4 color and 1 for the alpha channel. Okay, this is very nice. It is already a much better result. We'll improve it a little more, but first I'll remove the now redundant color assignment above these lines. This is what we don't need anymore. Okay, so we'll make use of the previously unused contrast parameter by applying the power function. By the way, this function isn't defined for negative values in GLSL. So we'll handle that by wrapping the input with the max function. So let's go before the final color assignment right here. Heat equals pow of max of heat and 0 and to the power of contrast. Okay, yeah, this looks even cooler, or maybe even hotter, I would say. And finally, we can perform the finishing touch by smoothing the result with the smooth step function. So it will be very simple. Heat equals smooth step of 0, 1, and heat. Okay, yeah, very nice. Now we can admire the final effect and then experiment with the parameters to see what kinds of variations we can create. So let's get back to the inspector. And as I said, contrast and emission are working. So let's increase the contrast or decrease it. And let's change the emission. Now it looks like it's hotter. So we can, for example, simulate things like the surface of a star or sun or something like that if we just play with the correct parameters and do something with it like slowing it down. So now it's a very slow lava boiling, and zoom out, zoom in. I believe there are nice combinations for anyone. Thank you very much for watching. Today's tutorial was a bit longer than usual, but it's true that more sophisticated effects require more complex code, which is not always easy to describe or explain. I am personally glad that I had the opportunity to experiment with functions I never used before, and I hope you find the final result useful. Thanks to the use of bitwise operations and a relatively low number of iterations, the computation is very fast, so we don't need to worry that using this lava effect will cause our game to stutter significantly. Anyway, thank you once again for watching all the way to the end. Take care, good luck with your game projects, and I'll see you in the next video.